Chemistry occurs when we have collisions, but the question is, what is colliding? What needs to crash into another thing in order for there to be chemistry occurring? And the answer is simple. The constituents of the chemical reaction, atoms or molecules, must collide into one another in order for there to be a chemical reaction. Without these collisions, there can be no chemical magic. There can be no chemical change. To help demonstrate this point, let's take a look at the following chemical reaction, a very simple one that serves to demonstrate exactly what's going on. We have these two BRNO molecules that are going to react and form two NO gas phase molecules, nitrogen monoxide, and a Br2 gas phase species. But let's take this chemical reaction apart and look at exactly what it's telling us. The two BRNOs can be written in the following way. We can separate them. There are two of them there. And so the first one is necessary, as is the second, as part of the reaction. And what occurs when these two things react, or what's produced, are two NO species, nitrogen monoxides, and the Br2 gas phase species. I like this representation because it serves to demonstrate how a collision is actually going to occur. We have, on the left-hand side, two reactant species. One BRNO crashes into another BRNO to form the products NO and Br2, three molecules of product species. Now, there are a couple of possibilities that we can imagine. Actually, there are an infinite number of collisions that could occur, but I'm going to, today anyway, have us consider the following two collisional possibilities. Let's say that we've got a BRNO molecule that is going to be crashing into another BRNO molecule, all right? So let's say that this molecule is heading in this direction, and let's say that we have another molecule, another BRNO molecule, heading in this direction, and I'm going to write the molecule as if it has been reversed. This one is O, and is still in the middle, and Br is off to the right. These are the same molecules. The order that the atoms are in is important, but reversing the order does nothing to change the identity of the molecule. Now, the second collision that I'd like to think about is similar in that we have a NO, and it too is traveling downwards because it's soon going to be involved in a collision, and what it's going to crash into is another BRNO molecule that happens to be in this particular orientation. So we've got two molecules both heading towards one another, and there's going to be a collision. Now the question is, which of these two collisions is likely to give us the products that we observe in the balanced chemical equation? And what I'd like us to do is to focus on the Br2. In this case, the product needs to, the product has the two Brs from the two molecules we started with attached to one another and broken free of the two NOs that were there as well. So as we examine the two possible collisions that I have here, notice that on the left-hand side, the Br is kitty corner, on the opposite corner from the Br of the second molecule. When these two molecules collide, there is going to be a collision, of course, but the Brs are not going to be colliding into each other. Or more simply, the Brs don't touch each other, and there's no hope for a Br2 product to form. On the other hand, we have on the right-hand side for that collision, we see that as part of this collision, what we're going to have are Brs that will collide with one another. In this case, the Brs do touch as part of the collision process. And therefore, what we can say is that between these two collisions, This is going to be an ineffective collision because it doesn't bring the atomic parts of the molecule in contact with one another in a way such that it's likely the Br2 is going to form. It only makes sense then that on the right-hand side, this collision, which does bring the two BRs together, is what we would call an effective collision. An effective collision is one that has the molecules that are colliding with one another in the correct orientation, such that there's going to be a product likely to form. Again, we don't really know what the product is until we look at the answer. We have to look at the actual product species that are formed on the right-hand side in that chemical reaction. We have to peek ahead a little bit and recognize that it's Br2 that's forming. And if Br2 forms, then as part of the collision, the two BRs must certainly contact one another in the process. The first possibility doesn't allow that because the BRs are on the wrong sides of the molecule. But in this case, the BRs do touch, and it's likely that that would be an effective collision. Keep in mind that collisions have all kinds of different orientations. We've looked at two extreme possibilities here, but at least this is a possibility that would permit the Br2 to form, and again, there are all kinds of possibilities that we can imagine. Now, I've introduced the concept of an effective collision, and it would be a good idea to write down exactly what that effective collision is all about. And effective collisions occur with orientations that favor product formation. Okay, that makes sense. That's what the example above was referring to. However, it's not enough that an effective collision occurs with the right orientation. We can also say that effective collisions occur with enough energy to produce bond making and breaking. Okay? Energy needs to be part of what's considered when we talk about effective collisions. And the energy part of this is something that we need to examine next. Okay? Now, the way one typically looks at the energy considerations as we discuss effective collisions is we do this graphically. And so I'm going to create a simple little graph here, which is a graph of potential energy versus reaction progress. Now, what do I mean by reaction progress? I mean, let's imagine what happens as reactants are converted into products, just like that. Okay, so the reaction progress coordinate, the x-axis in this case, is simply the progress that the reaction makes as reactants are converted into products. Now, the potential energy of the reactants, okay, the potential of the energy of the reactants starts, in this example anyway, kind of high. And what this is referring to is the separate NO-Br molecules that we have. And let's write that in the same order as we had before. Take a peek up there really quick. Let's see. BRNO is the way we're going to write that. Okay. BRNO. And we have two of them, after all. They are colliding with one another, and so I'm going to try to show you that here with these little arrows. There we go, one colliding with the other. Notice that the orientation of these is such that it's likely to be an effective collision, but we need to consider this other factor, and that is the energy required to make and break bonds. Now, what's kind of interesting about this is that as you bring these two molecules together, as they collide into one another, what they experience first is the repulsion that exists between their mutual between their respective electron clouds. You know, the framework of the molecule is situated within a swarming mess of electrons that are part of the lone pair and the bonding electrons. But needless to say, the framework has a lot of electrons that it's embedded in, and it's these electrons that actually that are felt first. And as you know, two electrons, or electron clouds in this case, they have the same charge. They're going to repel. And as a consequence of this, the potential energy of this situation is actually going to go up as a result of the electron-electron repulsion that goes on. We see an increase in the potential energy of the system. These two molecules are actually fighting us at this time. As we try to bring them closer and closer such that chemical change can occur, the collision also brings about an increase in the potential energy because the electrons simply do not want to be near one another and are fighting you, repelling each other along the way. Now, at some point, we actually reach a position, and we'll do that here in green. At some point, we reach a position that's called the transition state. Now, the word transition suggests change, and that is exactly what happens at the transition state. The potential energy reaches a maximum value, you see. And at this maximum value, the two BRNO molecules are now quite close together. Let's show that. We've got the Br, we've got the N and the O of the first molecule, and we've got the Br and the N and the O of the second molecule. And the electrons that have been repelling are now being balanced somewhat by the situation's energy and the making and breaking of bonds. Now, in this effective collision, the effective collision with the right orientation has led us to the transition state. And in the transition state, we actually see a bond being made between the two BRs. After all, we know what the answer is. We're going to have Br2 at the end of this. And at the same time, we have to have the separation of the Br from the remaining NO part of the molecule. And so in this case, and in this case, we have bonds that are being broken. Bonds that are breaking. Okay? In the transition state, we bring the two molecules close enough together that the desired bonds in green are being made, and the bonds that need to break are being broken. During this process, the situation is such that it may actually reverse itself and go back into reactance, or, more interestingly, the energy of the system, as these bonds are made and as these bonds are broken, takes a sharp and sudden decrease and lands over here on the right-hand side where we have products. And the products in this case will be the Br species, that's Br2, and we'll have an NO left over, and we'll have another NO left over because the bonds that had connected the NOs to the BRs have broken, and the bond that connects the BRs has been made. And so we see now we have the desired products. Okay? All right. Well, put products here. And we've got reactants over on the left-hand side. Okay. Now, as part of this process, you'll notice that we had to climb the hill to get up to the transition state. And once we've climbed the hill, we have a sharp and sudden downhill slide as the products are actually formed. It's interesting to look at this graph without all of the clutter, and so I'm going to redraw it here for you, just so that we can mark it up a little bit more. It's going to look as much as I can like the graph that I just drew for you, but we just need some space to look at how various parameters are measured. So here is the graph, and there are the products. We've got products over here, and we've got reactants over here, and we've got potential energy on the y-axis. Now, as the reactants, which begin here, approach the transition state, we are forced to climb a potential energy hill. The energy required to get to the top of that hill is important. Without that energy, we cannot reach the transition state, and we cannot ever hope to see any kind of change. What we call the height of that hill is we call it E sub AF, where E sub AF is known as the forward activation energy. The forward activation energy is the amount of energy it takes to get up to the transition state. Okay, the forward activation energy. Now, we also have the situation where we can talk about the reverse of this process, where we would look now at the height of the hill. If we were to try to convert products back into reactants, why, we'd have a very tall hill to climb. This is also known as an activation energy, and I talk about this as being the reverse activation energy. If you want to convert products back into reactants, then you're going to have to, in this case, you're going to have to climb a steep and much taller hill. So we have the forward activation energy, which takes us from reactants to products, up the activation energy hill, up to the top, the transition state, which is still up there, and then down, or we have the reverse activation energy. Now, if we concern ourselves less about the actual activation energy in this case, but more with the position of the reactants and the products, why, we see that the reactants begin with a fairly high potential energy, but the products end in this location right here. The products have less energy than the reactants did. And again, what happens in between is really not important. It's true that we have these activation energies for both the forward and the reverse directions, but the actual energy change of the reactants in comparison to the products is independent of activation energies. This change, which is a downward change, it starts high and it goes low, is the delta H for the reaction. The delta H for the reaction. And in this case, it's pretty obvious that the delta H is actually a value that is decreasing. The enthalpy of the reaction decreases. The delta H is therefore a negative value. Okay? And negative values, negative delta H's, are always associated with reactions that are exothermic. Okay? An exothermic delta H tells us that the system is giving up energy. And this energy that's lost is lost as the reactants are converted into products. If you examine the figure carefully and assume that the activation energies are all positive values, then the delta H of the reaction can actually be related to the activation energies in the following way. The delta H of the reaction is the reverse activation energy minus the forward activation energy, and this is again assuming that both activation energies appear as positive values in this graph. All right, now to finish this off, let's look at one other possibility. If you've followed what we've done so far, you can probably anticipate what's going to come next. You see, we've looked at an example where the reactants started high and the products went low, but we can also imagine this situation where reactants are converted into products and there's a steep upward slope, and we can see here that the products are now actually high. So let's include all of that. We've got reactants on the left and we've got products on the right, and this is the reaction progress, and we've still got potential energy on the y-axis. But now we've got a forward activation energy that looks something like this. I'll draw a line here just to identify the peak. We still have our transition state up at the top, and this distance right here is the forward activation energy, and in purple we've got the reverse activation energy right here. Very small. Try to squeeze it in. Okay? And in red, we can imagine how the reactants compare to the products in this case, and so I'm going to extend the reactant line. Again, this is independent of the activation energies that we have. In this example, the reactants start with an energy that is low, and they end as products with an energy that is high. And this is the delta H in this case. And it's easy to see here that the delta H now is greater than 0 and positive, and therefore this describes the situation where we have an endothermic reaction. Recall, an endothermic reaction is one that is going to require heat energy from us as we try to fuel this reaction to make it happen. And in this case, we need to have a positive value, and let's see, are we going to? The reverse reaction, you know what, I think I've got something backwards here. Rather than start over, let's go back and have a look here just to be sure that the numbers work the way they're supposed to. Catch this, I believe what I've got is something that is reversed, and indeed I do. I need to make sure that I come up with a negative value up here, and so this is unfortunately backwards. Let's try it again. I'm going to draw a line through that, and we're going to fix it. The delta H for the reaction in this case is going to be equal to the forward activation energy. There we go. This is going to give us the negative sign minus the reverse activation energy. So make a change in your notes. That's not quite right. But fortunately, that same recipe will work for us here and will generate the positive sign for the endothermic reaction. And so with that little oops out of the way, we can now use the very same recipe to determine the delta H of the reaction. We don't need to modify the order that we're subtracting, and if we do that, because E sub A is smaller than E sub A reverse is smaller than E sub AF, we will get the positive value, which is what we would expect for an endothermic reaction. All right? Now, as you can imagine, the activation energy is an important part of this process. You see, if you don't have the activation energy, and I'll use this figure to indicate this. Let's say that you start with a reactant that has this energy, and it only has enough kinetic energy to take it up the slope that far, at which point it turns back around. It may have, the reactants may have had the correct orientation, and the collision looks good at the start, but we don't have, in this case, enough energy. So I'll say not enough energy for chemical change. If you want chemical change, why, you have to supply, the collision has to involve enough energy to take us from the bottom all the way up to the activation or to the transition state. And if we've got that much energy, why, we'll have enough energy for chemical change to occur. But if the collision doesn't involve enough energy, why, even though the pieces may have the correct orientation, they won't have enough energy for change to occur. So when do molecules and atoms have the amount of kinetic energy that is required? And so what we need to look at is how many molecules actually have kinetic energy sufficient to get up to the transition state, to equal the forward activation energy. And so what we're going to look at next is something that's called the Boltzmann distribution of kinetic energies and abundances. That's a fancy way of saying we're going to look at all of the molecules in a particular sample of matter, and then we're going to imagine how many of them have this kinetic energy, how many of them have that kinetic energy, how many of them have enough kinetic energy to actually undergo an effective collision, and how many are moving just too slow to dash any hopes that change might be observed. Now, the Boltzmann distribution, a very famous historical distribution, has on its y-axis the percentage of molecules that have a particular kinetic energy. And the y-axis is their kinetic energies. Okay, so the Boltzmann distribution is going to show us how many molecules, on a percentage basis, just to keep the numbers easy to work with, how many molecules have kinetic energy equal to 0. Now, if you imagine the population of molecules that we're talking about are in a room, say the room where you're sitting right now, where you're breathing air in and out. Now, I think we all probably already understand that molecules in the atmosphere are moving with velocities. They're actually crashing around, careening around. But some of them are moving very slowly. Many of them are moving with higher speeds. Some of them are moving ridiculously fast. And the Boltzmann distribution is going to tell us how these all look. For example, there are very few moving with velocities 0. That is to say, there are very few molecules in that room right now, filled with atmosphere, that are just standing still. However, as we look at in fact, I'm going to make that one blue. I've got a reason for that. You'll see it in just a second. As we look at progressively higher kinetic energies, we find that more and more and more molecules have these progressively higher kinetic energies, and the distribution reaches a maximum at some point, you see. All along the way, as we've looked along this distribution, we've seen greater and greater numbers of molecules, greater percentages of molecules that have higher and higher speeds. And at this point right here, the distribution reaches a maximum. And then what we find is, as we look for molecules that have even higher speeds and kinetic energies, the distribution falls off. There are actually fewer and fewer and fewer molecules that have these kinetic energies higher and higher amounts. In fact, if you go way out here, the distribution has approached the x-axis so nearly that we can say for all practical purposes there aren't any molecules with kinetic energies and velocities at these very high levels. Now, if we imagine that the activation energy for my reaction, I'm going to back up from that a little bit. I'm going to move that line up just a wee bit. Let's see, right about there. Let's say that the activation energy threshold is, for the forward reaction, E sub AF right here. In other words, if a molecule crosses that line, if a molecule has the speed and thus the kinetic energy that it has and is greater than the activation energy, why then we have an effective collision, if the orientation's right. But as you can see where I've drawn the line at the moment, there are no molecules, I'll call that 0 molecules, there are no molecules with that kinetic energy such that they can reach past the activation energy and actually create a successful collision possibility. So in this case, we can say that the temperature, or and this has to do with the temperature, a cool temperature, which is why I drew it in blue, we can say that the temperature is too low in this case, and that we have no molecules with kinetic energy greater than or at least equal to the forward activation energy that we were hoping to exceed. And so in this case, as there are no molecules, well maybe there are one or two, but not enough to matter, there are no molecules with sufficient kinetic energy, we can say then that no chemistry, no effective collisions occur. And therefore, no chemical change takes place. All right? Now we can actually change this. I've already suggested what the change might be. Let's consider a temperature T in blue, which is, actually less than a new temperature. This Boltzmann distribution actually changes slightly and subtly and in an important way if we look at the distribution of kinetic energies that molecules have at higher temperatures. Now, the total area under the curve has to remain the same because we still have to make sure that everything adds up to 100%. But at higher temperatures, the distribution begins to broaden out somewhat. It doesn't reach up quite as high, and it peaks at a point further out. But most importantly, what happens is that it tails off. We'll extend that line out just a little further. It tails off and shows us that we have a significant amount or a significant number of molecules now that have kinetic energies greater than the activation energies. This area is equal to the number of molecules, let's call that percentage of molecules, to be consistent with how the axis has been developed, the percentage of molecules with their kinetic energies that is now actually greater than the activation energy of this reaction. Now we have a small but significant percentage of molecules whose kinetic energy is enough that if they're colliding and they're crashing into each other with the right orientation, now they have the kinetic energy and the crashing potential such that the collision will be effective. Okay, so now we have the possibility that we can have an effective collision. All right, an effective collision, and likely chemical change takes place. All right. If you were to go to lower temperatures, why, you'd make the situation even worse. I'll draw a lower temperature curve in purple just to show you the effect. In this case, the distribution peaks a little bit more highly, but peaks more quickly. And as a consequence of that, there is even less chance that molecules will have the kinetic energy required to get past the activation energy to reach the transition state and to actually produce some chemical change.